Nothing. Okay, so let me share my screen and we'll show the syllabus. So here it is. Can you all see this okay? So September 6th was Labor Day, September 8th was Wednesday, and here we are on September 10th. And so we're going to start chapter 5 today and hopefully go through that. And we may finish it up in class. Well, we'll do a little review. And I may have you do a practice test in class on Monday for the first 5 chapters. We'll see. Maybe I'll delay that to Wednesday. But anyway, okay, so we will be in class on Monday. And I think I looked it up and it's, well, let's see, I'm not sure what room we're in. All right, well, let's get rid of the syllabus. And then we'll pull up the slides. And we will do chapter 5. And these are on Blackboard if you want to follow along. Come on. Yeah, can't move the stupid thing. We'll see what this is. Okay. All right. Okay. It's chapter 4. So that's no. No. Okay. So that's not it. All right. So let's get rid of that and see if we can do this one. 5. Ah, perfect. Okay. And now do that. All right. Can everybody see that okay? Yes? No?
Yes, sir.
Yes. Yes.
Is chapter 3 ready to go? Yeah. So I have on the quizzes. So the problem is that I can't directly edit the quizzes. I have to submit stuff to Great River Learning and they have to actually do the edits. And they corrected the answers, but in some cases they didn't change the verbiage on the question. So that still led to some confusion. So I'm working it. It turns out it takes 2 or 3 shots to get it done. I think 4 is fine. I think they should all be corrected now because I have submitted all the corrections multiple times. But I'd have to go through and check it. I have authorized additional things. So at this point, I mean, don't worry about it. You know, I'm not going to ding anybody for the first 2 or 3 quizzes, but hopefully we'll be on track here soon. We'll see. All right, chapter 5. So first off, a truth table. This is not just a theoretical thing that's not going to see again. Truth tables have tremendous functionality, and you're going to be dealing with them for a long time to come. Every device has a truth table associated with it. Usually in the data sheet, complex devices have things that look a little different than truth tables, and some of them will list state machines, which we're going to get to in the last part of the course. But truth tables are a big deal. They are functional. They have great functional value, and we use them a lot. And you're going to be stuck with truth tables for a long time. So don't think of a truth table as as just a theoretical thing you don't have to really worry about. It's a guide to the design of hardware. We use it as sort of our guiding star when we do hardware, particularly a combinational design. We're always checking our design to make sure that it, in fact, does what the truth table says it's supposed to do. Secondly, even when we do state machines, we may very well use either a SM or a state table, very similar to a truth table, for the same purpose. So we're going to use these things, and it's really a guide. the hardware can be implemented a whole lot of different ways. So the truth table is sort of a singular thing. But once you get the truth table done, now you can actually turn it into hardware a whole bunch of different ways.
Hey, Professor.
Yeah.
You're kind of cutting in and out. You're like you're going far and then coming back in. So I don't know if your mouth is not close to the microphone or.
Yeah, I'm sitting right here in front of the computer. I don't know. This is just not super optimal, but fortunately, this is the last day we have to do this. I can't do it from home on Fridays because I have to be here for my Micro 1 lab. So, but so I'll try and sit on this side. Maybe the micro, I know it picks up over here, so maybe it'll be a little better. Okay. Yeah. All right. Sorry.
Yeah, that's much better.
Okay, that's good. So if I sit over here, I think it is a little better. Okay. So remember, once we have the truth table, we have lots and lots of options about how we're going to actually turn it into hardware. And all those options can give us exactly the same result. The truth table really says for any given set of the independent variables, say ABC, what's F, what's the output variable? Now, and we can have multiple outputs and we can have more than 3 inputs, but we're sort of, we're sort of starting with the training wheels on the bicycle. And so we're using, a small number of independent variables, say 3 inputs, and we're using usually not too many outputs, maybe 1 or 2, or later on we'll do the projects, we'll have 5 or 6 or 7 outputs, or maybe more than maybe 10 or 12 or even 16 outputs. All right, so the truth table is pretty definitive, right? Every entry gives a entirely predictable output. But we can implement it with a whole bunch of different gate choices. We can use ands and ors. We can use ors and ands. We can use nands and nands, nors and nors. We can use exclusive OR gates. We can do lookup tables. We can use ROMs. We can do all sorts of stuff. Multiplexers. There's a lot of ways of implementing the hardware. And in many cases, we have completely identical solutions, even with the same gates, that we can implement the gates, the same set of gates. We can just implement that same set of gates several different ways and get completely equivalent solutions that are slightly different. So a lot of different ways of implementing the truth table. We can do the minimum solution. We can do a solution that involves more gates than we actually have to have. Sometimes we have to do that if we're going to eliminate some hazards. All right, so just keep in mind, the truth table, though, it's really your guide. Lots of different ways of implementing it. But once you get the truth table set up, you have a deterministic relationship between your independent variables and your dependent variable. All right. So here's an example. Let's take a truth table. So how many independent variables do you see here?
3.
That's right. A, B, C are the independent variables. We have one dependent variable, and that's F. And we've chosen some value for F for each one of the rows. First, for row 0, it's 0. For row 1, it's 1. For row 2, it's 0. For 3, it's 1. 4, it's 1. 5, it's 1. 6, it's 0. And 7, it's 1. Now, where did we get the value for F in this truth table?
From the independent variables?
Well, once we put it in here, then the independent variables determine which row we're in, which determines F. But how do we decide that the first row would be 0, the next row 1, the next row 0, and so forth? So this is always a point of confusion, and that's why I'm asking the question. We essentially get this from our customer, or I like to say we get it from God, okay? So you don't have to figure that out. That's what comes from your customer. Now, you do have to translate your customer's desires into the desired output in the truth table. And that can be tricky because sometimes the customer doesn't speak in truth tables, the customer speaks in English, or maybe even Chinese or some other language, and you have to translate that into a truth table. And that's where you can get yourself in trouble. So we'll talk about that in a minute. But first we're going to see, given the truth table, and you're given this F. So you get it from someplace, from your customer, or you take what your customer said and you come up with it, but it basically is given to you. It's your starting objective, and it's given. Your boss says, Joe, I want you to build me a circuit that implements this value for F given these independent variables. And that's your marching orders. You don't get to change F, okay? You're stuck with that. But you can certainly change how you implement it. All right, now, one of the things we do is we talk about min terms and max terms, and that's one way we can implement a truth table. Now, every row has a min term. So here's the first row. It has ABC in it, and A is 0, B is 0, C is 0. And the min term that represents that row is called A prime, B prime, C prime. The next row, A is 0, B is 0, C is 1. The min term for that row is A prime, B prime, C. Notice these terms represent an AND gate with A prime ANDed with B prime ANDed with C prime. This would be A prime ANDed with B prime ANDed with C. Down here we would have A ANDed with B ANDed with C, because they're all ones here. And if you go through here, it should become pretty quickly obvious how we're doing this. Say here we have A, B prime, C prime. So if the A value is 1, then we don't prime it. But if it's 0, we do. So this would be A, not primed, but B prime, C prime. This would be A, B, C prime. And this would be ABC. And this would be A prime, B prime, C prime. And so every row has a min term. Every row also has a max term. And the max terms represent an OR gate. So so instead of having them ANDed together or multiplied together, as in A prime, B prime, C prime, we have them ORed together with little pluses, like A plus B plus C. Now notice in the max terms, instead of A prime, B prime, C prime, we have A non-prime plus B non-prime plus C. And down here where we have ABC, we have A prime plus B prime plus C prime. And it turns out that if you take all the min terms and you invert each one, you get the max term. But now listen to this very carefully. When we solve the problem, the max term solution and the min term solution are exactly equal to each other. They are not the inverse. But it is true that for any particular row, the min term is the inverse of the max term and vice versa. And generally, I use this to help me solve these problems, because sometimes I get confused when it's easy for me to write the min terms. I think A prime, B prime, C prime, because they're all 0 here. And now I have to remember to flip them to get the max term, A plus B plus C. It's a little confusing. So a lot of times I'll actually write the min term and then just invert it in my head, and that'll give me the max term. And it keeps me from making mistakes. You don't have to do that if you don't want. But it is true that the min terms are the inverse of the max terms and vice versa. But it is not true that the min term solution is the inverse of the max term solution. The inverse of the min term solution would be the opposite. So if F is supposed to be 0, the inverse of it, F would be 1. And of course, that would be the wrong answer for any particular row. Now, how do we get the min term and the max term solutions to be equal when the terms are the inverse? Well, the answer is we don't use all the min terms for the solution. We don't use all the max terms for the max term solution. We only use certain ones. So when we want to write the SOP form for a given truth table, we only use the min terms where F equals 1. And you can see, yeah, I don't know if you'll let me do that. Yeah, well, maybe. So when we want to do the SOP solution, we only use the min terms where F equals 1. Well, where are they? Well, I put little stars on all the min terms that we would need. We don't need the first one because F is 0 there. We do need this one. We don't need this one. We do need this one, this one, this one, not this one, and we need this one. So that gives us a min term solution. Well, we'll see it in a minute. When we want to use the max term solutions, we only use the rows where F is 0. So if you see, we never use the same row for the min term and the max term solution. So here, F is 0, we use the max term if we want the max term solution, and we use this row, and we use this row. But if we're doing the min terms, we do this row, this row, this row, and this row. So that's how come they can always be equal to each other and not the inverse. All right, so what would the min term solution be? Well, it's in the green. Let's see if I can move this up. Yeah, there we go. So the min term solution would be A prime B prime C plus A prime B C plus A B prime C prime plus A B prime C plus A B C, which would be this term A prime B prime C plus this term A prime B C plus this term A B prime C prime plus this term A B prime C plus this term A B C. Now look at the max terms. Now how come we have 5 min terms but only 3 max terms?
Is it because it becomes more precise?
Well, that's an interesting thought. So the answer is there are only 3 rows where the output for F is 0.
I was about to say that.
And there are 5 rows where the output for F is 1. Now, it doesn't have to be that way. It could be anything. But it turns out in this particular problem, we had 5 1s for F and 3 zeros.
Yeah,
And
so
so-
that would have lead me to my other question. So for this example, this is how the outcome would be, but it could have the infinite various of outcome based on what you're trying to accomplish, right?
Yeah, not infinite. It's finite because you only have 3 independent variables. So with 8 rows, you have a total of 256 possible combinations.
Okay, well, yeah.
But it's a good number, big number. Yeah, that's right. Exactly right. Okay, so that's good. So we have 3 terms for the max, and notice these terms represent, each one of these terms is a OR gate. And each one of the green terms in the min term solution, the SOP solution, is an AND gate. Notice that the whole expression is one big output OR gate with 5 inputs. And here the whole expression is an output AND gate with 3 inputs coming from each of these 3 OR gates. So both of these represent a 2-layer net. The SOP has input AND gates, 1 output OR gate. The POS has a bunch of input OR gates, in this case 3, and 1 output AND gate. So, all right. Now here we get to, back to where we get the F, okay? So your customers don't typically talk in truth tables. If they do, it makes your job a little easier, because then you can take the truth table and go do your design. And as long as you implement the truth table, you're good. And if your customer's not happy, you just show them the truth table and say, this is the truth table you gave me. My circuit exactly implements this truth table. What's your problem? Well, you might want to be disrespectful, but you say it implements the truth table. That's what you told me to do, and that's what I've done. And that's pretty much the end of the discussion. The problem is the truth table is, the customer didn't give us a truth table. He gave us a bunch of words to describe what he wanted or she wanted, and we had to translate those words to the truth table. And the problem is there always can be ambiguities that come up, and I'll show you an example in a second. So you have in the truth table, the ambiguity is completely eliminated. Remember, truth tables are totally deterministic. There is no fuzziness about what you're going to get when you put in your independent variables. It's laid out, set in concrete. But when the customer describes this problem, there may be some ambiguities, and so you should ask questions, because you want to remove all the ambiguity, because when you do the truth table, it's going to be deterministic and there's going to be no ambiguity in it. And if it doesn't quite do what you wanted, then you're going to have an unhappy customer, and that's bad for repeat business, and it's bad for your company reputation. So you definitely need to make sure you get this translation from English to Boolean correct for your customer. And this usually means that you have to look at the logic expression and think about adding and eliminating parentheses. All right, so let's look at an example. So the original English is the alarm bell will ring if the alarm switch is on and the door is not closed, or if it's after 6 p.m. and the window's not closed. Okay, that's what the customer told you. I want the alarm to ring if the alarm switch is on and the door is not closed, or it's after 6 p.m. and the window's not closed. Now, when we have a description of not closed, we usually add a prime. Because then if B prime is 1, that means the door is not closed. So that would mean that B is 0. So B would actually, in this case, represent the door being open. Or rather, if B is 1, means the door is closed. If B is 0, means the door is open. B prime, if it's 1, means the door is not closed. So since we had the English say not closed, that we used B prime here. Okay, now we did the same with D, not closed. If we hadn't put the not in here, then we wouldn't have used the prime. We would have just used it. If he had said the door is closed, then we would have said B. Well, but that would have changed the meaning. Anyway, that's why I put the primes there. Okay, so how would we turn this into a logic expression? So we would say Z equals what? A ANDed with B prime, ORed with C ANDed with D prime. Like that. Z equals AB prime plus CD prime. Now, if you're the smart engineer, you look at this and you're sitting with the customer having this discussion, and you kind of write that down in your notebook and you think, okay, where are some possible ambiguities? And you look at it, you maybe add parentheses like this. Now, somebody look at these two and tell me what's the practical difference? Or better yet, you can be thinking about that. Let me give you an example. You're the smart engineer, so you ask your customer this question. You go, supposing you're working in your office late one night, and it's kind of hot in your office, and you open the window. Your door is closed, but you open the window to cool your office down, but it's 7 p.m., after 6, right? 7 p.m. The alarm's going to ring, and the alarm's going to ring if you use this equation, whether or not the alarm switch is on. Is that what you want? Oh, no, I want to have the window open and not have the alarm ringing the whole time. That would be horrible. Okay, so this is what you actually want. You want the alarm switch being on to be absolutely necessary, and then one of these other two conditions. Either it's after 6 p.m., or either the door is open, or it's not closed, or it's after 6 p.m. and the window's open. Then you want the alarm going off if the alarm switch is on, right? Yeah, that sounds good. But you see, if you built this, the first time your customer had a hot night and he was working late and he wanted to open the window and the alarm rang and he reached over and he turned off the alarm switch and the alarm kept ringing, he might be unhappy with you. Because see here, the alarm will ring on the condition of just C being true and D prime being true, which would be after 6 p.m., that would be C true, and the window not closed, that would be D prime true. Doesn't matter if the door is open or closed or the alarm switch is on or off, still going to ring just based on this condition. And that may not be what he wanted. Now, maybe it is, I don't know. Maybe, no, I don't want my employees opening the window after 6 p.m., regardless, whether it's hot or not in the office and they're working late. Okay, fine, then we'll do this. So you see how you need to, there can be.
Is it?
Go ahead.
I was gonna say, is it because on the first one that it's either one of them has to be on the or, and then I'm seeing the second one where you have an and where both of them have to.
That's right. That's exactly the difference. Right. So you can see how when you write a logic expression, it really does put it in cement. When you write it in English, it's a little ambiguous, right? There's a little potential confusion. about what is exactly meant. And that's actually true all the time. So that's why as a smart engineer, you have to reduce it to one of these two, and then you realize, there's a problem here. Let's see, what's the implication of putting these parentheses in here versus not here? Well, one is that this will turn on the alarm all by itself. And the alarm switch could be off and the alarm is still ringing. Maybe he doesn't want that or she doesn't want that. So let's ask that question. And then we'll document it in our notebook and we'll document his answer. And then later on, we'll send him an email with confirmation about what we discussed and how we concluded things and make sure, yes, this is in fact consistent with our discussion and you're in full agreement. And then if he's unhappy with what we produce, then it's on his head, not ours. I mean, and we're willing to change it. He's just gonna have to give us a little more money to get the job done. So, and he'll be happy to do it because he realizes he made a mistake, not us. Whereas if we make the mistake, guess who has to eat the money? So, all right. So the real implication of these two different implementations is that it has a different real world impact. And that these logic expressions are deterministic. They're totally set in cement. They're not, there's no ambiguity in them. The ambiguity is in the English description. All right. So once you reduce your design to a logic expression or a truth table, the outputs are completely determined by the inputs and the ambiguity is gone. So to be successful, you have to have captured exactly what the customer wanted. And then obviously, if you finish your design and then you need to change it, that's going to be a lot more costly than if you can change it before you get started at the very beginning. And so that's why this is really important, get that truth table right and get buy-in from the customer, make sure you've asked all the questions and you've eliminated any ambiguity that might be in the customer's mind or in his verbal expressions or written expressions of what he wants. Okay, so now we deal with these min and max terms. Let me move this down a little bit so you can see this. So here's a circuit. Now tell me, you guys look at this circuit and tell me if this is an SOP or a POS form.
SOP.
So tell me what does an SOP mean?
Sum of product.
Right, right. So that means that we're adding up our multiplied together terms.
So what is the product of sums? Because it's the AND gate.
Yeah, we're actually multiplying these terms together because of the AND gate here. And these are actually OR gates. I guess that could have been confusing because they're ugly OR gates, but anyway, that's what they're supposed to be. So this is really product of sums. And this is confusing notation. In fact, they couldn't have made it more confusing for students if they had tried. Because in this case, it's product of sums, right? So the P stands for product. It comes first, but it's actually the last gate. And the sum gates, which are the OR gates, they come first. They're the first layer. So when we say product of sums, what we really meant was we're putting OR gates into one
AND gate.
AND gate, yeah. So we should have called it ORs to ANDing. I don't know, but anyway, the standard nomenclature is product of sums. So it's just really tricky. So just remember, it's kind of backwards and it's very confusing. And we're using this product and sum when we're not really talking about multiplying or adding. We're talking about OR gates and AND gates. You just have to really fight through that confusion. Once you get used to it, you'll be fine. But it's a little tricky because it is confusing. And if you're a little confused, don't feel bad. All the students that have come before you have had the same exact confusion. It is confusing. It was done, I think, to be confusing. All right. So let's look at the next thing. What if we have a truth table where the customer says, okay, it's possible that A, B, and C can be all zeros, or 001, or 011, or 100, or 101, or 110, or 111, but it's never going to happen that A is 0 and B is 1 and C is 0. And you don't have to necessarily know why, although it might be good to ask. But once you fully understand the problem, it may just be the case that that will never happen. And you know, this can happen on an assembly line. This can happen, you know, on all sorts of control situations. There's all sorts of times where some of the conditions just won't ever happen because they're illogical, like the conveyor belt moving at high speed and the gate at the end is locked closed. Well, that would be bad. So you would never want that to happen. So you'd say that's never going to happen. And so you have other circuitry that keeps that from happening. So now you have to have something that's going to use this truth table and generate this output for F, for 0 here, 1 there. We put a question mark here because this row is never going to happen. So what's F supposed to be? Well, it doesn't really matter, right? And then 1 here, 1 here, 1 here, 0, and 1 there. So what do we call this row? We call this row a don't care. And it is
What?
we call it a don't care.
Okay.
And it isn't really that we don't care. That's kind of another confusing terminology. It is that we don't, it is that it'll never occur. Therefore, the output can be whatever we want because it's never going to actually happen. And so for that reason, we don't care what, well, we do care what we choose it to be because we will specifically choose it to be either a 1 or a 0, whatever makes our solution simplest. And it will have an effect on our solution. So we definitely care about what it is. It's just that it's never going to happen, so we can choose it to be whatever we want. So another example of confusing nomenclature in the logic design world. But we call them don't cares, and you'll call them don't cares. But just remember, the formal name is incompletely specified. So what it's saying is we specified F for all the rows except for this row, where A is 0, B is 1, and C is 0, which happens to be min term 1, 2, 3, and max term 3, 0, 1, 2, max term 2 and min term 2. And it turns out we can either use min term 2 or not, or if we're doing a max term solution, we can either use max term 2 or not. We can include it or get rid of it. Now you're thinking, well, why would we ever want to add one? It's just an extra term. Yes, but it might make our switching algebra, we might allow our switching algebra to simplify it to a simpler expression. And so you'll see that. All right, so this is incompletely specified. So the other thing I want to introduce, and we'll come back to this in a minute. The other thing I want to introduce is standard form shorthand notation. And so this is how we usually write these things. So what is this shorthand notation? Okay, so we have shorthand notation for our min term, and we have shorthand notation for our max term. The min term, we use the sum sign because we're going to OR together our min terms. Each one of these terms represents an AND gate where we're going to OR them all together or sum them all together, okay? And so we look over here. So everywhere F is a 1, we would have to have that min term. In this case, min term 0, the first row is row 0. So min term 0, okay, so we put it there. The next row is row 1. We need that because F's a 1 there. We put a 1. And then we don't need row 2, so we don't have a 2 over here. We don't need row 3, but we do need row 4, and we don't need row 5, 6, or 7. So our min term shorthand notation solution for F is F equals the sum of the little m's, and then we put them in parentheses, 0, 1, and 4. We do the same thing with the max term. We say F equals the product of the big M's, and which big M's do we need? Well, we need all the zeros. So this is row 0, 1, so we need row 2, 3, 5, 6, and 7. 2, 3, 5, 6, and 7. Now, if we have don't cares, then I'll show you that in a second. So say 3 and 6 are don't cares. We'll put an X for the don't care. Means this row will never occur, so we can pick F however we want. So when we do that, we change our notation a little bit. For the shorthand min term notation, we still have our 0, 1, and 4, but now we have don't cares for 3 and 6. And here we took away the zeros and put in don't care. So now we only have zeros in rows 2, 5, and 7. And we multiply that times the product of the don't cares at 3 and 6.
So even though you're saying that you don't care about that row, you're still gonna put it into your calculations?
Well, no, we write it this way so we know that we have this option to use it or not. So,
Okay.
so we're gonna look at this. So here's our example. Okay, so we're given this truth table. So I guess it's the same one, 0, 1, yeah, it's the same truth table, except we have a don't care for row 3. Okay, 0, 1, 2, 3. So we have a don't care for 3. So first off, how would we write the shorthand the notation? So we'd write for the min term, we'd write it's the sum of m 0, 1, 4 plus the don't care and 3. Or for the max terms, we'd write it's the product of 2, 5, 6, and 7 and times the don't care of 3. So that's how we write it. But now what should we actually do? Let's actually do it and see. So let's say we want the simplest possible solution for this truth table. How do we get that? So this is where you have to do some work. Okay, so first we solve it without the don't care, which means for the min term solution, we let the don't care equal 0. And then we solve it with the don't care, which means for the min term solution, we let the don't care equal 1, because we can let this x be whatever we want. So let's say it's 0 first. We'll write the actual min term. And that gives us 2 equations. So we actually have to do 2 equations here. So we have to write the SOP expression 2 ways, once where x is 0, once where x is 1. And then we have to write the POS expression 2 ways, once where x is 0 and once where x is 1. And that's going to give us 4 possible expressions, and we have to pick the simplest. So here they are. If we let x equal 0, then we would have b prime c prime plus a prime b prime when we sort everything out. Now, I'll work this on the board Monday so you can see how that's true. But just take my word for it today, because I can't work it out here in my office. I don't have a projector. So here's this simplified. We actually wrote out all the min terms. We would have a prime b prime c prime plus a prime b prime c plus a b prime c prime. And it turns out we can combine these first 2 and get BC, and we combine the first and the fourth one and get b prime c prime. So that's how we simplify. But we'll show you that on the board. But we're just using our simplification term. And in fact, we're only using one of the simplification terms. We're using S1.
Professor.
Yeah.
Does it have like additional videos for us to watch to kind of grasp this a little bit easier?
Well, I'll go through it on Monday on the board. I think it'll make sense then.
Oh, okay.
So yeah, so don't freak out. It's really pretty straightforward, but I'll show you. Okay, and then the max term notation, same thing. Well, okay, so then let's take the don't care as a 1. Well, it turns out it just changes it a little bit, but we still get basically the same number of literals, same number of terms. So it doesn't really change the cost of our circuit. Still going to be 2 AND gates, 2 input AND gates, 1 output OR gate, 1 output OR gate, or 1 2 input OR gate. Same thing here. We have 1 2 input AND gate, 1 2 input, another 2 input AND gate, and 1 2 output OR gate. So these have exactly the same cost. So it really doesn't matter. We could take the don't care as a 1 or take it as 0. We're going to get the same hardware when we're all done. What about the max term? Well, if we take the don't care as a 0, we get b prime plus c quantity times a prime plus c prime. But if we take it as a 1, which means we don't include it in our max term solution, then we get b prime times a prime plus c prime. Actually, I think this is taken as a 0. But anyway, so this is taken as a 1, this is taken as 0. Anyway, now if you look at these 4 solutions, which one gives you the simplest hardware? 1, 2, 3, or 4?
4.
That's correct. Excellent. And can you tell me why would you say that?
I assumed from the previous, when you were trying to explain with the process of your customer, and then I just assumed that B prime would go into. It was assumption, basically.
No problem. So here's the answer. So let's count up the gates. We have 1 OR gate and with 2 inputs, and 1 AND gate with 2 inputs. B prime is one of the inputs, and the output from the OR gate is the other one. So this only has 2 gates, and all these have 3 gates. So it saves a gate.
So almost like simplification, kind of.
Yeah, so these translate directly to hardware. You can just write these circuits, right? We have an AND gate here with B prime and C prime. We have an AND gate here with A prime and B prime. And the 2 outputs of those AND gates go into 1 2-input OR gate. And that OR gate gives the final solution, F. And the same thing here. Here we have 2 input OR gates. This one with B prime and C going in. This one with A prime and C prime going in. And they feed into a single AND gate with 2 inputs to give you F. But here, this B prime doesn't have to go into a gate. In the first layer, you only have 1 OR gate, and then B prime skips that first layer and goes into the output AND gate. So there's only 2 gates in this solution if you do the minimum solution. All right. So number 4 is the least cost. And that's great. Let's see, give me a second. John, I'll call you back in 15 minutes. John, call you back in 15.
Dr. Morton, how are you?
I'm good. I'm doing class. I got to call you back in 15 minutes.
15 minutes, all right, thanks.
Okay, sorry. All right. Now, so hopefully this gives you an idea. So notice, one stupid little don't care. Look at all the work you have to do to figure out the simple solution. You have to solve this truth table 4 different ways. Turns out, if we use the K-map, you could just look at it and see the answer immediately. And that's why K-maps are so much fun for students and why switching algebra is such a thing.
Is that another tool that we use too?
Yeah, we're going to cover that in the next chapter after the first test. So as soon as we do the first test, then we're going to jump right into K-maps, and you'll be a lot happier because things will be visual, and you'll be able to use your natural ability, your visual system, to see the simplification. But here you have to use switching algebra, and it's a little bit, so it's painful.
So when we do start to go in-person class, will we have, would we be able to like dibble and dabble and mess with these type of things?
What is that?
Yeah, so, well, hang on. Oh, Martin. Hello? Yes. Go ahead. All right. Okay, anyway, I swear, all these interruptions. Okay. All right, go ahead, ask the question again. Sorry.
What I was asking, I was like, when we do start going in person, would we be able to get the opportunity to like mess with these actual gates, like dibble and dabble in it, so we could see a better understanding, get a better understanding of it?
Yeah, so that's what the Logic Design Laboratory 2511 is all about. Are you taking Logic Design Lab this semester?
No, I'm not.
Yeah, so that's the idea, but unfortunately, they never have enough room in that course for everybody. So there's always people taking it after they've taken Logic Design. But I think you'll get the hang of it. It's kind of fun to actually use the gates, but I think you'll get the hang of it. Okay, let me just see. Press on. So here's an example. Now this one, we have 4 variables, A, B, C, D. So now instead of 8 rows, we have 16 rows. because there's 16 possible combinations of A, B, C, and D. You can think of it as 4 bits, 2 to the 4th, 16. All right, so, and here we have another F. In this case, I didn't put in any don't care. So this one is completely specified. No, it's not, there's no, oh, I take it back. I did put one in here. I lied. So row 3 has a don't care. All right, so we'd have to do the same thing here. So first we write the minterm expression. So that would be without the don't care. And then we simplify it. Now, how do we simplify it? We simply use S1, and that is that's XY plus XY prime equals X. So if we look at this, and again, I'll do it on the board so it'll make sense. But if you look at this, we have A prime, B prime, C prime, D prime. And here we have A prime, B prime, C prime, D. So notice the D, all the other variables are exactly the same in both these terms, except for the D. The D changes. And since the D changes, we can drop the D using S1, and we can just write, we can combine these two terms to A prime, B prime, C prime. Now we're allowed to use them over again if they can help another one. And actually, the first one and this one can also combine, and we'll drop the B, because we have A prime, C prime, D prime in both terms, but the B is a B here and a B prime there, so we can drop the B. So now that gives us A prime, B prime, C prime plus A prime, B prime, D prime. And then here we can combine it again and drop the A. And then here we can combine it. No, we can't combine this one with any of these, but we can combine this one with this one and drop the B and the B prime. And then we can combine that with, we can combine this one with this one and get ABD. And when it's all said and done, if we do the combining correctly, we can get down to B prime, C prime plus A prime, C prime, D prime plus ABD. That's with X equals 0. And if we make X equals 1, then we get down to this. And you can look at these two and realize this is simpler. Now, I did not consider the max term solution here. So if I really wanted to, if the question was, what's the best min-term solution, then I've answered it. It's this one. But if the question is, what's the simplest solution for this truth table, we don't know yet because we didn't look at the max term possibilities. And we'd have to, and there's 2 of those. So we you know, there could be confusion about that. All right, I think I'm gonna stop with this and we'll come back and we'll rework those examples on Monday, and I'll do it on the board. So I'll show you exactly how we use theorem S1 to simplify those equations. And we'll do a couple others as well. All right, any last minute questions? And make sure you check, go to ASAP and check and see what room we're supposed to be in. I don't remember off the top of my head, but
Okay.
yeah, so I'll send out, I'll check it and send out an email just to remind you.
Professor, somebody had a question. Just wondering if you want us to, or if you're encouraging or requiring memorization of all the laws and their duals.
So I talked about that a few lectures ago, and what I basically said then, and what I still kind of maintain is, if you work through a bunch of problems and you get a level of familiarity so that you kind of know, you know, you have a pretty good idea of all the theorems, but you haven't memorized them, that's fine, because I'm going to let you refer to them when you do tests and work problems. So I'll give you the theorems, but if you haven't become familiar enough with them that you've almost, but not quite necessarily memorized them, then you probably won't be able to use them very effectively anyway. So, you know, somebody asked about the video I posted for Wednesday. I don't think, let's see, well, I'll look at that. I'm pretty sure all the videos on Blackboard that are under the folder F21. I think they're all the ones that I've done with you guys. But if not, I'll go back and look at them and check. But I think they're all correct. But it's possible that something got mixed up. I don't know. Possible.
Yeah, and just reverting back to what I was.
Maybe I put a micro one video in by mistake. That's possible. Okay, that's what that could be. Okay, I'll check and see. I think there was one class where I didn't. I can't remember what class it was. I don't know. There might have been one where I didn't record it, so maybe that's what got confused. Okay, I'll double check that. All right. We will see you then on Monday in person. I'll send out an email with the room number and yeah, looking forward to it. All right,
Lovely.
bye.
Bye.